Okay, welcome guys to lecture 10. I hope you're doing well during the coronavirus pandemic and you're keeping your social distance. What we're going to do today is we are going to discuss a new topic in the database world, which is the topic of logs and recovery. This is a very interesting feature that distinguishes the database technologies from all other kinds of software, as you will see. When discussing this feature, we are actually covering three of the major components of a database engine: the buffer manager, recovery manager, and the log manager. These three components work together kind of in sync to ensure the consistency of the data. And what remains afterwards for us will be the transaction manager and how transactions are actually run. And that will be the topic of the next lecture. So what's the issue here? The issue is with databases, you get a very neat feature that your data is always protected. This is why people use databases in the first place. I can give you many examples of instances I had or incidents I had where I lost my data. For example, I could be editing it happened once to me. I was editing a piece of code in Eclipse, and Eclipse crashed. And when I started Eclipse again, the code was gone. Another time I was writing a document in Word, and the current went off. And when the current came back, the last few paragraphs I wrote just completely disappeared. Okay? Now, these types of problems in the database world, they simply do not exist. The notion that your data is lost or gets corrupted, like in the example we are seeing in front of us here. If I have an employee table and I have these names of people and the age in front of each name, there's no chance that I opened the table one day and I got this ridiculous age number, 3,421 years. Because what database engines give you, if a database engine is built properly, is the protection for your data, that your data will always be valid. This is very important from a business point of view, because imagine if you're maintaining your customers' data and the products they just bought, and suddenly the data gets corrupted. So instead of someone buying a single TV, you ship him 10 TVs because somehow your data got corrupted, and the guy opens the door and here is his 10 TVs that he ordered while he ordered one TV. Okay, so this kind of inaccuracy or data corruption is not tolerated in the business world, and it shouldn't be tolerated anywhere. Okay, so we will see throughout this lecture how can we get this done. This is a very nice feature. We will go a lot in a lot of details about how this is implemented, and the nice thing is this actually started in the database engines, but now there is even file systems that tries to do what we are going to describe later on in the lecture. Now, this goes back to a topic that you've learned in Database 1, which is this notion of integrity of the data. Okay? In fact, there are many features of relational algebra that is there to protect the integrity of the data. The very notion of a key, okay, that you have a key that uniquely distinguish a row, is to maintain the integrity of the data. Because if a primary key allows duplicates, means it's not unique. What that means is when you query a specific row, or you're looking for a specific row using its key, you're gonna get two or more rows, which doesn't make sense. Okay, for example, if you have a citizens table and the key is the social insurance number, you want to ensure uniqueness because every citizen should have his own social insurance number. Now, what you actually get with this is an integrity feature. It's not just that, oh, it's nice to have or it's important to have. you can say that the data has integrity, or that the data integrity has not been violated. Okay, the data is meaningful and usable. I mean, that's what really integrity is all about. The same thing for defining domains for columns. Okay, you can always attach a domain to a column and say that the values that will go in this column has to belong to this specific domain. Like, for example, color, you would say it's either red, blue, or green. What you're doing here is that you're adding an additional rule that will be enforced by the database engine to make sure that the data has integrity. You don't want to see the color purple, for example, because it has no sense, it has no meaning for your application. And what the database engine gives you is this ability to associate a domain with a column, which means that if you try to insert any other color apart from red, green, and blue, an exception will be thrown, or an error will be thrown from the database engine. Okay. Now, this notion of having features in the SQL to maintain the integrity of the data is very important. But sometimes you might miss, when you're actually building or defining the schema of a table, certain rules, okay, because they are more like business oriented. Like, for example, the last point I have there, it says no employee should make more than twice the average salary. Okay, now in modern database engines, in the latest one, actually this could be enforced by adding a constraint, which could be even a SQL procedure that you write that retrieves the salary, calculates the average, and it gets triggered. So it's basically like a trigger that gets triggered before you do an insert. Okay, but historically, this was not always there. So sometimes certain rules has to be maintained in the high-level language that's accessing the database, if the database engine does not have a feature to enforce it. But luckily nowadays, database engines are so advanced that even for such a rule that I've written at the last line, actually it could be enforced by adding a trigger that runs before an insert is executed. Okay, so all these features exist in the relational world, or in SQL, to be more specific, to try to maintain consistency of the data. Now, this brings us to the notion of consistency. When I talk about a consistent state of a database engine, I mean that the data satisfy all the constraints that were encoded. So, a consistent database is a database that will always be in some consistent state. So it's always in a consistent state. It moves from one consistent state to a new consistent state to a newer consistent state, and it's always in a consistent state. Between those consistent states, there is nothing. So there is no notion of moving from a consistent state to an inconsistent state to a consistent state. It's always moving from a consistent state to a new consistent state. Okay? Now, this is very important, but you have to realize that this is limited by how good you have designed the schema for the database. You have to encode all the possible constraints. So, for example, if you have a column called color and you define it as a varchar, say, of 6 or of 5, and you don't add a constraint that the color value has to be red, green, or blue, anyone can input any color that consists of 5 letters. In fact, anyone could input any letter, any word that consists of 5 letters. If you made it varchar of 5, that is not even a color, like the word door. Okay. Now the data integrity now is questioned, but the problem is coming from your definition of the schema that is incomplete, that you didn't add the constraint. So when we talk about a database being in a consistent state, I'm assuming that you've done your work and you've added all the constraints that you can add using the database engine that you are using. And if that is the case, then what you get as a guarantee from the database engine that it will always leave you or take you from one consistent state to a new consistent state. It will always leave you at a consistent state. Now this might sound like a bit theoretical now, but you will see where will this be used shortly. Now again, just to stress the point, the constraints is up to you to add them. Okay, I have here an example. Let's look at the first point that says when salary is updated on a promotion, it shouldn't be the new salary greater than the old salary. Okay, it should be like this. Okay? Now, shouldn't it be like this? Of course, it should be like this. But if you don't add a constraint that when you are actually applying a promotion, that is the case, someone might add a promotion by a negative number, so the new salary is less than the old salary. Now, that's not the fault of the database engine. It is your fault as a programmer that you haven't added the right constraint. Okay? Or like the second point, when the account record is cancelled, shouldn't be the balance equal to 0. Okay? Of course it should, but again, that is your responsibility to add in the SQL a statement that says, when an account is cancelled, then you should zero the balance. Okay? By itself, the database engine does not understand business logic, and consequently, you cannot claim that, okay, the database engine is not maintaining consistency of the data, because really it's your fault that you didn't add the right constraint. Now we come to the very important topic of transactions. This word transaction appeared first in the history of computer science in databases. One of the most important kind of innovations in the history of systems, which is a branch of computer science. Okay? This is how it works. When a SQL statement arrives into a database engine, as we've mentioned, it goes through several translations from parse tree to logical tree to physical tree. And the output of the physical tree, or the physical plan builder, which is a physical tree, is placed in a container. The container is called a transaction. This is a very important piece of innovation. And the transaction, this container, is responsible for taking the database engine from one consistent state to a new consistent state. So the way things work is that the container mechanism supported by transactions or introduced by transactions is the guarantee for us that we go from one consistent state to a new consistent state. Okay? Without transactions, the whole model just collapses. Okay? We are doing a lot of things based on the notion of a transaction, as you will discover through the coming lecture as well. Now, so again, transaction starts with a consistent state. When it ends, we have a consistent state. Okay, we have moved from one consistent state to another consistent state. In the middle, we were executing a transaction. A transaction will never violate the consistency. In other words, it will never end with an inconsistent state. Whatever happens inside it, it's transparent to us. But the point is, when it finishes, we are now in a new consistent state. And if it doesn't finish, then as if it never ran. So we are back at the old consistent state. There is nothing in between the two states. Okay? Now, the interesting thing, and this will not be really clear to you now, except when we talk about how transactions are built, each transaction is seeing the database engine as if it is the only one running in there, which is not true at all. At any single instance, there could be tens of SQL statements getting executed. But the nice thing about transactions is that they don't just encapsulate the SQL statement or the physical plan corresponding to the SQL statement, they also run as if no one else is running. And all of them are like that. So you could have, at a single instance, 50 transactions running at the same time. Each one of them thinks that it's running alone. And the nice thing is that each one of them leaves the database in a consistent state. There is no footstepping, if you would like to think of it this way. No one will damage anyone else's data. And we will spend some time talking about that later on. Now, going back to the issue of constraints, there are a number of ways constraints can be violated. The first one is that you have a transaction bug. You wrote the wrong SQL. Okay? You wrote the wrong SQL, basically, and that's your responsibility. The violation comes from your side, not from the database engine side. Sometimes, and this is rare, but it does happen, that the database engine itself has a bug that violates the constraints. Okay? Now, more commonly, you could have a hardware failure. Database engines or servers dedicated to database engines. Think, for example, of the database engine that is running behind the Souq website or Jumia website or Amazon website or anything like, that kind of scale of operation. The number of transactions they are getting per second could be quite big, could be in the tens per second. So it could be like 50 or 60 transactions per second, or even more. Now, that means that the hard disk is working all the time by writing updates to the tables. So ultimately, this decreases the lifespan of the hard disk. And one of the first things that's going to happen when the hard disk starts having a problem is some sectors will be damaged, because the head that reads and writes from the sectors damaged the sector while doing the mechanical movement above the sector. Now, when it fails, we consider that as, when the sector write or read fails, we consider that as a hardware failure. So you might be writing a part of a row or a row in that sector, and it just fails. The write operation will fail. Okay, so obviously you have an issue there, and we would like to protect our data from such a situation. Okay, there is even more higher level ones, and this is the ones that's always of concern to us, which is things like the example I have listed in the last point. That we have a data sharing issue. I have two transactions written by two different programmers. One programmer has passed a SQL statement to give 10% raise to all programmers, so he's basically giving raise to himself, and the other one is changing the title of programmers to system analysts. Okay, so if the transaction 1 kicks in and finishes before transaction, if transaction 2 kicks in and finishes before transaction 1 runs, the guy who's trying to give raise to himself in transaction 1 will not succeed, because there are no more programmers in the system, okay, or in the database. However, if transaction 1 runs first, well, he's lucky, he's going to get a 10% raise. Okay, now what if there is an action overlap, that parts of transaction 1 runs and parts of transaction 2 runs? So now we have a problem, and we will spend some time discussing this later on. Okay, so we have mechanisms against this scenario where, say you have 10 programmers, 10%, 5 of the 10 will get the raise, and then transaction 2 starts running. So it will change all the titles to system analyst. So 5 will get the raise and 5 will not get the raise, because now the title is system analyst. We will have a protection against this, complete protection, so we don't run into this scenario. Okay, but if we don't have such a protection, which is going to be the topic of the next lecture, we are running into trouble, because that's what happens all the time in a database engine, that you have many transactions running where at least a subset of them are touching the same data, or touching the same row or the same page. So we will handle this later on. So we will spend some time talking about all of this. Okay, chapter 17, 18, and 19 in your textbook are all dedicated to these topics, which is error handling, error recovery, error prevention, and transaction support. Okay, so we'll talk about all of this in detail. Now, we have to build a model according to which we work when we talk about recovery. Okay, so our model goes like this. We have two types of events. We have desired events and undesired events. Desired events is what you plan for. Undesired events, we will classify them to expected and unexpected. Before we go into there, let's understand one thing about how things run. Computers are built according to a very old model that was designed back in the 1950s called the von Neumann model, or the von Neumann architecture. Now, in the von Neumann model, or the von Neumann architecture, and von Neumann is the guy who actually developed this model, and this is how all CPUs are made, or all computers or motherboards are made. You have the hard disk, you have memory, and you have the CPU connected together by a bus. You cannot change things on the disk. You have to change it in memory if you would like to change it. What that means is you have to read it from disk, put it on the bus, put it inside the memory, which is designated there by M, and this is how at that point in time the CPU can kick in and start modifying the data in memory. When the modification is done, it's done in memory. It's not done on disk. What that means is after the modification is done, you have to take the data back and put it back on disk. Okay? Now, number of issues here that you have to understand is that the bus, which is this line connecting the disk, the memory, and the CPU, is a bottleneck. But we will live with this. We cannot change it, because this is how the model is designed. And there is another issue, which is that the changes are always happening in memory. And I think I already mentioned this several times in the course, that changes are in memory. You don't change things on disk. We cannot open the hard disk and write on it. It's not like a piece of paper we can write on it. We change things in memory, and then we take them and put them on disk from memory, which will create all kind of problems, as you will see. It does, because when you are editing your document in Word, in WinWord, okay, or when I was writing my code inside Eclipse, the code was actually in memory. So when the Eclipse crashed, it didn't have a chance to save it to disk. So when I opened Eclipse again, the code was gone because it was just in memory. It wasn't on disk. Okay. Now, modern applications try to work around this by doing the following. This exists. This feature I'm going to describe exists in Microsoft Office. They have a thread that runs in the background that kicks in every, say, 10 or 15 seconds, and will do what's called an autosave, which means it's going to take all your content from memory and put it on disk. This at least reduces the amount of data that you will lose if the current, say, suddenly goes off. But it will never be a complete protection, unlike database engines, because between the last time the autosave worked and the time the current went off, let's say the autosave worked at time 12:31, and then the current went off at time 12:32. Okay, so if the autosave is running every minute, well, you will lose the last minute of work. Okay, so it does help, but it's not completely bulletproof. You still lose some of your data, and you're losing it because of the von Neumann architecture. The model itself basically means you got to put things from disk to memory, work on them in memory, and then put them back on disk. So let's go to this notion of desired versus undesired events. So desired events is what you expect, what you code in SQL, what you code in stored procedures. Okay. So hopefully you will always be running a database engine that performs as you expect. Okay, in terms of desired events. Now, undesired events, we are talking about things like system crash due to memory damage. The memory itself could be damaged. The CPU itself could suddenly burn, or it resets itself. So the machine just boots, and you get this blue screen on Windows that says, Windows.system.32 faced the problem and would like to reboot, something like this. Okay, or you could be working and the current simply goes off, as sometimes it does happen. Okay, but these are all expected events in the sense that obviously any piece of memory have a lifetime. And especially when you're doing a data-intensive operation like working with databases or installing a database on a server and you have lots of traffic, ultimately the hard disk and the memory, will just start to have physical damages. Okay, at least the hard disk. The memory will sometimes have damage because of manufacturing problems as well. Same thing for the CPU. If it gets, say, the CPU has a fan mounted on top of it, if it suddenly the fan stops working, it would just take you like 2 hours before the CPU completely melts. Okay, so the fan is very important and it should always be working, but you have no control on that. It's an electromechanical device, and current goes off is obviously a normal scenario anywhere in the world. Okay, so everything else is undesired and unexpected. Obviously, it is undesired. We don't want it, and unexpected because we are not normally designed to think of it. Unless you are a paranoid person, you would not think what I'm referring to as unexpected. Okay, like for example, you get this crazy employee who hates the company and decides to steal the hard disk. Okay, well, actually, in banks they have mechanisms or policies or regulations against this, or to protect against this. For example, because it's always tempting if an employee doesn't have enough, I'm not sure how to describe it, like ethical reinforcements. What about stealing someone's money from the bank account if you're working in a bank? And the way around this, or the regulation to handle this, is that bank data is always replicated on many servers. So if an employee decides to transfer $1 million from someone's account to his own account and then take off, well, it will be actually discovered from the other copies of the data. Okay, or I got an employee who's crazy who goes to the server room and just set it on fire. Okay, so this is again unexpected, undesired, and this is also something that banks, for example, and big and governments as well have regulations to protect against such incidents. For example, they would have more than one data center. and they would not give all IT staff access to all data centers. So they would have separate IT teams, so they have things under control. Okay. Also unexpected is if the server room just by accident is set on fire, so all your hard disks there in the servers just go away. Okay, they just burned. And again, the redundancy here is the solution to handle this problem. But all of these things are actually not something we talk about in this course. This is a mix of security plus other things like data warehousing, which is not really a topic that we're talking about here. So, what can we do to handle expected but undesired things? Well, there are many techniques that is not really, again, database technologies, but systems kind of approach. For example, you could replicate the disk storage. You could run software in the background that checks that everything is okay in terms of the health of the hardware. So there is software that does what's called memory parity checking. Basically, it goes to the memory. Let's say you have 6 GB of RAM. So it goes to those 6 GB, and byte by byte, it will write a bit stream and then read it throughout the 6 GB. And if there is any corruption in one of the bytes, say it will write in the byte 1 1 and the rest is 0, and then when it reads them it's 0 1 and the rest is 0, so it knows that this byte is actually damaged, and it will print a report to the IT to say, okay, you got a memory corruption in your RAM. Okay, there's also similar kind of software for checking on the health of the hard disk. Okay, but again, all of these guys are things that are outside the database technology kind of control. They're more like systems, system tools to guarantee that the server is always running. Okay. Now we come to the stuff that actually is of concern to us, which is the mechanisms that exist inside a database engine to make sure that there is no data corruption, and that is done by ensuring that we move always from one consistent state to a new consistent state. Okay, the example I will always refer to here, what if you're working and the current goes off? Okay, like you're doing transactions, people are buying stuff from your website, and someone is buying, say, a TV, and while he's doing the transaction, or while your code is doing the transaction on his behalf by taking money from his credit card, recording his address, putting a shipping request, and decreasing the stock of TVs you have, while you're doing all of this, midway the current goes off. What happens? Okay, now what the database engine gives you as a promise is that you will always be in a consistent state. So you will never be in a situation where you charge his credit card and you don't ship him the TV because you didn't record in the transaction or in the business logic that you have to ship him. You didn't put the shipping order, okay? Or that you put in the you charge his money, you put the shipping order, but you don't decrease your stock by 1. So now you don't know that you actually have sold 1 from your stock. So instead of 10, there's supposed to be 9 now. Okay, so all of this you got a protection against. Now, to understand all of this, the first point we need to understand is how is the database engine architected so that it solves this problem. What you see on the right side is a disk that has pages. Those pages belong to some table. And the way things work inside the database engine, that's what you see on the left. A transaction comes, the translations happens. Now you have a physical plan. The physical plan is ready, so a transaction gets created, and the physical plan steps are placed inside the transaction. The transaction, you can think of it as if it's a program. When it's actually running, it's not going directly to the disk to read the pages of the table, which is what you're doing in mini project 1. What is actually happening, the transaction is always talking to the buffer manager, and the buffer manager is responsible for accessing the hard disk. So all transactions, even if you have 100 of them, they're all talking to the buffer manager. No one goes to the disk directly. Okay, so this is a very important kind of isolation mechanism that we are building here, which is the buffer manager, that we want to protect access to the disk. So it's centralized, and this enables us to do a lot of interesting things. For example, if we notice that a page is frequently requested, we can keep it in memory, okay? And the buffer manager's responsibility is to write it to disk in the appropriate time, okay? So we will define 4 operations: input and output, and read and write. So input and output is between the buffer manager and the disk. Read and write is between the transaction and the buffer manager. So this is the picture I'm interested to show you. The transaction, when it would like to read a specific row or page, it will call the buffer manager and tell it read X into T. Okay? So X has to be a good enough descriptor, either a page or a row. Now, if a transaction modifies X, it will tell the buffer manager, I want you to write X into T. Sorry, T into X. Okay? So T is like temporary from inside the transaction manager, and sorry, inside the transaction. So read is read X into T. So T is actually a local variable that's created by the transaction. Now, when the transaction is done, it will call the buffer manager and tell it, okay, I want you to write back T into X. So in other words, as if it's telling it, write it to disk. But it's not really doing the writing to disk. The buffer manager is the one that's actually going to do the writing to disk. Okay? When the buffer manager is doing the writing to disk, it's calling a method called output. So it will output X and put it on disk. Okay? And if the buffer manager would like to read from disk, it will call a method called input. So input will actually fill in X with some data from the disk. Okay? So the transaction will never call input or output. It's always calling read and write between it and the buffer manager, or really in the buffer manager. So let me give you an example of this. So one of the things we're going to talk about later on in detail is this notion of transactions, because actually when you code SQL, you can write an add transaction, okay? And usually it will be something like start transaction, and then you put a number of SQL statements, and then end transaction. But I will postpone this discussion to later on. Let's just say that you've sent the SQL statement, update table R, set A equal to A by 2, B equal to B by 2. Now, for your information, any SQL you send to the database engine, even if you don't have it encapsulated in a transaction like the one I have done over here, it will be encapsulated in a transaction because this is the normal way of running things. Now, in terms of steps, what are we really doing is that we are multiplying A by 2 and B by 2. Okay? So, as you know, what's going to happen, we have already described before. The SQL is translated to parse tree, to logical tree, to physical plan of choice. That is put inside a transaction. If you go and open the source code or if you open a transaction while it's running in memory, if we can actually do this as a virtual exercise, that's actually what you're going to see as steps. This is what I have written over here. So I'm going to read it and try to comment on what is this. So it says read A into T. So that's retrieving the value of A and putting it in T, and then multiplying T by 2, and then writing T back into A, and then read B into T, and then multiply T by 2, and then write back the new value of T into B, and then output A and output B. See, these are the actual steps that you will see inside a transaction. They're almost like assembly code for databases. Now, who generates this? It is the transaction manager, which we didn't talk about yet. It's actually going to take a physical plan that you have decided, or the database engine have decided is the optimal one, and translate it to this assembly-like instructions. Now, the logic is the same as you have written in the SQL. Okay, I am multiplying A by 2 and B by 2, but this is a more stepwise kind of programmatic approach to doing that. Okay, now I will assume here for simplicity, because again I cannot introduce lots of details in one shot. I will assume here that A and B are just two records in a single row. So you just have a task to update just two values. The old value of A and B are 8, and the new value after we run this successfully should be 16 and 16. Okay? Now, so what we are doing again, we are changing it in memory. We're not changing it on disk. And after the change is done in memory, we write it to disk. Okay? Now, here is the example I was referring to before. What if the current goes off? What if after you do the output, now the output is done between the buffer manager and the disk. So output A means write the new value of A, which is going to be 16, you write it in disk. And then you get this failure because of a current going off. Now, you have a problem. When you start the database engine again, the new value of A, or the value of A is going to be 16, and then the old value of B is going to be 8. Now, according to our way of thinking, we want the database engine to move from one consistent state to a new consistent state. So let's give them names. The first one was the old consistent state, which was 8 and 8. The new consistent state, which would have been, if this transaction completed successfully, is 16 and 16. 16 and 8 is not a consistent state. This is a state in between, and we don't like in between states. You either go from old consistent state to new consistent state, or you stay at the old consistent state. Okay? But we don't like states in the middle. So this is an example of an inconsistent state that we're trying to avoid. Okay? Either we make it 8 and 8 or 16 and 16. Because that's what the logic of the transaction is trying to do. Make it 16 and 16. So if we make it 8 and 8, as if we never ran the transaction, which is fine. It was never there. And if we make it 16 and 16, well, exactly that's what the transaction was trying to do. Okay? So, to achieve this, and this is really what makes transactions a very important kind of milestone in the history of computer science, we need this notion of atomicity. That we need to treat the transaction, regardless of the number of steps that exist inside it, as an atomic thing. It's like an atom inside a nucleus. It's only one of it. So there's only one there. So atomicity means either you execute all the steps or you execute none. If you execute none, as if it was never there. If you execute all the steps, as if you went to a new consistent state, or actually you are at a new consistent state. Okay, so atomicity is actually what made transactions extremely popular in the history of computer science. With transactions came the notion of atomicity, that we need things to be atomic, either runs or doesn't run, either it exists or it doesn't exist. Okay, so how are we going to do that? What we're going to do to achieve atomicity is we are going to keep a log of things. We are going to track which transaction is running, what is it doing, what's the old value of the data it was trying to change, and whether it's done or not. Okay, because for us a done transaction is a happy fact. Okay, an undone transaction is a problematic situation we have to handle. Okay, so this is the role of the log manager in the database engine, that it's logging things, it's tracking things, and it will maintain these logs on disk, just like the different data we are maintaining on disk, like the pages of the table and the indices, nodes, and so on. We also have these logs that are being updated by the log manager. So inside a log, what you have are simple commands that tells you that a transaction started, a transaction is doing something, and a transaction is done. Usually the name would be like start, some T, where T designates a transaction. So it says, the saying, this transaction is starting. Like if you see the log at the bottom right, it says start T1, which means T1 has just started. Okay. Now I'm using here simple names just because of the space, and I got these from your textbook. So usually the transaction identifier will be a longer sequence of alphanumeric characters. Now the next instruction says transaction T, the one in blue, is modifying X and the value is so and so. So everything the transaction does will be written to the log. So T has to be a valid identifier for a transaction, which means it's a transaction that has already started. Like for example, if you look at the log, it says T1 is modifying A and the value is 5. Okay? And then if you look at the third statement in the log, that I have put at the bottom right. It says start, T2 has started, and then T2 is modifying B and the value is 10. T2 is modifying C and the value is 15. T1 is modifying D and the value is 20. And then T1 committed, which means T1 is done. Okay, it's not anymore there, it has finished. T2 committed, so it means it's done, it's not anymore there, it has finished. And then T3 starts, and this goes on. Everything is logged, as you have noticed here. Now, notice that there are interleaving of steps. So T1 starts, and then T1 is doing something, and then T2 starts, and then T2 is doing something, and then T1 is doing something. Why? Because every transaction runs in its own thread. So there's interleaving between transaction actions in the log. Okay? Now, some of you are taking the operating system course, so you know by now what is a thread. If you're not taking the operating system course, a thread is basically a way of running a program independent of other programs, and this gives us the illusion that all programs are running at the same time, while they are not really. Okay, so I will not really go further talking about threads, but what I want you to understand is that all of these guys are running at the same time, so there is a kind of overlap access to the log. All of them are accessing the log. When someone does something, it will, ultimately write it to the log, or the log manager will write it to the log on their behalf. Now, we will look at 3 types of logging. The first one is called undo logging. Okay. Now, this is the same sequence of steps we looked at before, but now we are adding to the picture the log. Okay. Now, the log is a file that will be written to disk that contains information about what's happening, just like what you have seen. Okay. Now, undo logging is all about history. So in undo logging, the goal is to bring the database content to an old consistent state if there is any anomalies of violation of constraints. Now, that is by looking at the transaction, or tracing through the transaction history, which is available in the log. So what you're seeing here is the log being active. The log manager is writing to it. How come the log manager knows that what is currently happening? It gets notification from the buffer manager that this specific transaction is making this change. How does it know that? Because remember, the transaction is going to call write and read in the buffer manager. So when T1 in the third step, it calls write T into A, it's writing 16 into A, the buffer manager notifies the log manager. Now again, this is undo logging. We are interested, the goal is to bring the database to the old consistent state. So what we're going to do is we are going to record the old values, not the new values. That's why you see in the log it says T1A8, which means T1 was trying to modify the record A, and the old value is 8. We didn't write the 16, we wrote the old value, which is 8. Now, this will continue on. Every time there is a write from the transaction to the buffer manager, the log is updated. And that's what you see here. Now, the same thing is going to happen to the B. And we see that in the log, it says T1B8, which means transaction T1 was modifying B and the old value is 8. And then when the transaction finishes, we see in the log a statement inserted by the log manager that transaction 1 has committed, which means it's done, it has finished. So this is an example of running the transaction along with writing into the log what's happening. Now, there's one issue here. Someone already might have thought of it. According to the von Neumann architecture, the von Neumann way of thinking, we make all changes in memory and then we put them on disk. So we ran into a problem that we were modifying the A and the B in memory, and before we were able to put them on disk, say the current goes off. So we run into an issue there, and we said the solution is to use a log and write down the changes, or specifically the old values of the changed records, so that we can track things. But someone might say, okay, but the von Neumann architecture, according to its way of working, even that log will be written to memory first and then put on disk later on. So what if the current goes off while we're writing the log? We really didn't solve the problem because we just moved it one level away from us. Instead of talking about the records having inconsistent data, now we have the records having inconsistent data, and the logs as well are not helpful because they haven't been written to disk, or maybe they have been partially written to disk. Okay? Now, here's how we're going to handle this. We will make sure to write the log in memory first. This is what the first point is saying. Log is first written in memory. Okay? And we are going to make sure to do something else. And if you try to think a little bit, about what should we do, well, the thing is, we can be writing line by line the log in memory and then taking that line and putting on disk, because that would be too much disk access. But we need to come up with a strategy to make the log useful for us, okay, so that we can actually use it to recover or take the database to an old consistent state if we need to do so. Okay? So I will give you some hints before we move on to the slides. When shouldn't we be doing anything? Well, we shouldn't be doing anything with the logs if the transaction has committed successfully. Okay? So that should be a hint to something, because if the current goes off and I start the database engine and I go and inspect the log and it says T1 started. T1 was doing something to A and the old value is 8. T1 is doing something to B and the old value is 8. And T1 is done. So I'm happy, because if in the log it says it's done, and if I have worked things correctly, then I shouldn't be doing anything, because T1 is done. It has made the changes and it went away, it disappeared, it's finished, it's done. So I shouldn't be worried. My problem will be if I see T1 started, T1 was doing something to A, T1 was doing something to B, and it's not done. And there you have a problem, because you don't know, okay, you know now that T1 is not completed. Maybe there were further steps. You don't know. So now you'll be concerned, okay? So it's important for me to have the log written to disk as fast as possible, but not necessarily with every line inside the log, okay? So I think I've given you enough hints. Let's move on and you'll see the rest of the details, okay? Now, this is the example I was just discussing. If you open the log and what you see is the two statements we had before, the T1 started, T1 modified A and the old value is 8, but you're not seeing the rest. You're not seeing what's in red here. You're not seeing T1 modifying B and the old value is 8, T1 commit. You're not seeing that, okay? Now, but when you go to the DP, you will see 16 and 8. A is 16 and B is 8. Well, you don't know what are good values, what are bad values, but what you know is T1 started and it didn't finish, because you cannot see a commit in the log, okay? So what that means is seeing the commit in the log is very important, because this tells you you don't need to do anything, because it has committed, it's done. But if you don't see it in the log, you don't know what was going on. It could have, completed all the steps, or it could have done 20 out of 50 steps. You don't have no idea. If you don't see the commit, you cannot make any judgment, except that T1 is problematic for you. T1 now is leaving you in an inconsistent state, and you got to use the log, whatever you have, to put the database back in a consistent state, okay? Now, let's talk about how can we actually get this exactly right. We are going to follow two rules in the undo log. The first one, let me read them. It says, if transaction T modifies X, then the log record TXV must be written to disk before, and I've highlighted that in red, before the new value of x is written to disk. Okay? So again, a transaction is modifying a specific record in a specific row before that modification is put on disk. It will be done first in memory and next on disk. It will be taken from memory to disk. Before we put that modification on disk, we write that row back to disk. We have to write the log entry for that modification in memory and move it to disk first, and then we move the row in the table to disk. Okay, so we're introducing here an order of doing things. We have to put the log entry on disk, not in memory, on disk. It will not be written obviously to disk before we write it first to memory and then take it from memory, put it on disk, but we have to write it on disk before actually we make the modification to the table. Okay? Now, the second rule, you will see shortly why. Now, the second rule says that if a transaction commits, then its commit log record must be written to disk only after the database record written to disk. Okay? This is kind of the reverse of the first one. What we're saying here that when a transaction is done, we're not going to write in the log that it is done until after it's completely finished. Okay? It has to be completely done. Like it's not there anymore. It has executed the last statement in its body, and there is nothing else it will ever do. Then we write to the log that this has been committed. So these two rules are very important because they will actually enable us to handle all situations that will arise because of any undesired expected scenario, like for example the current goes off. Okay, so let's see some examples. I have put the rules here for you, U1 and U2 at the top, just to refresh your memory, and the illustration at the bottom shows that the read and write is between the transaction and buffer manager, and input and output is between the the buffer manager and the disk. The steps are listed in the action column, and the value of t, the temporary variable I'm using to do the computations, in the second column. And you have the value of a in memory, that's m-a, and the value of b in memory, that's m-b, and the value of a on disk, that's d-a, and the value of b on disk, it's d-b, and you have the log content. Okay, now the log content, obviously it's in memory. Now, to solve the problem of wishing to always save the log as frequent as possible to disk, we are going to insert before, who is inserting that? The transaction manager who's making the transaction. We are going to insert an instruction called flush log, whose task or whose goal or whose functionality is to take the log from memory and put it on disk. So up till just before the flush log, the log was being written in memory, not on disk. Yet, once we execute flush log, we will take that log and entries and put it on disk. And also, to increase the chance of having our log frequently sent to the disk, we have another flush log after the last output, which is going to be at line number 12 after output B. Now, this is how things go. We start executing a transaction, read A into T, so we initialize T with 8, I'm now at line 2, multiply T by 2, I'm now at line 3, so you see T changing in memory, and then I write T into A, so A in memory is now 16, that's going to go from the transaction to the buffer manager, and then I will read T into B. Notice that the log is being updated because the buffer manager is sending notifications to the log manager telling it what's going on, who's reading, who's writing what. That's why when the transaction issued or a function call to the buffer manager write AT, you see the log entry getting modified. Now you have at line number 4 there's an instruction that says transaction T is modifying A and the old value is 8. Now, We're going to read b into t, multiply by 2, and then write t into b, and again upon this write you see the log getting appended with tb8. Finally we hit line number 8, and that's a flash log instruction. What that means is, let's take this log in memory and put it on disk. Notice that this is actually how we enforce the rule that we have discussed, which is U1, that we are going to write to the disk the content of the log before we modify the records of the table. The modification to the records of the table is going to happen in line number 9 and 10, which is output A and output B. The flash log appearing before them ensures that the log goes to disk. Now, output A will take the value of A from 8 to 16, output B will take the value of B from 8 to 16. And because we know that there are no more steps in this transaction, the transaction manager, when it was compiling these steps, inserted a flash log again. Now, then this flash log is an indicator that this transaction is actually finishing. So it will cause the commit instruction that we have added to the log to go to the disk. And notice that this will go to the disk after this transaction has no more steps. Really, this transaction has 10 steps, or if you'd like 9 without the flash log. So it has 10 steps basically. Okay, after it there is nothing. So only after doing the 10th step, which is output B, the commit T is written to the log. And because of the following flash log on line number 12, you have this commit T going to the log. Okay, so this mechanism of using flash logs 2 times, before the first output and after the last output, ensures the implementation of the 2 rules, which is that if a transaction T modifies X, then the log record must be written to disk before the new value. We get this from the first flash log. And the second flash log is enforcing the second rule, which is if a transaction commits, then its commit log record must be written to disk only after the database record written to disk. Now, let's go through the different scenarios to see if this actually going to help us, everything we have been describing up till now. Okay. Now, so to think about those scenarios, what I'm going to do is I'm going to assume that the current is going off after a specific line. So let's say the current goes off after line number 4. So after line number 4, we read A into T, we multiplied T by 2, and line number 4 was writing T into A. Did we modify anything on disk? No, because as you see, the value of A and B on disk, which is D-A and D-B, are still 8. The log has been, in terms of what was the content of the log after line number 4, in memory we had start T and TA8, but we didn't reach to the first flash log, which is line number 8, so the log will be empty basically. But then, are we losing anything? No, because A and B on disk are 8 and 8. It's the old consistent state. Now, let's assume the current goes off after line number 7. The same rationale I just described applies. We were modifying A and B. We finished modifying A and B in memory. It became 16 and 16. That's M-A and M-B. But A and B on disk are still untouched. The log has not been flushed because the crash or the current is going to go off after line number 7. So we didn't have a chance to execute flash log, which is at line number 8. So what that means, TA8, TB8, and the first statement start T will not appear on disk, and actually we're not losing anything because still A and B are still 8 and 8. Now, let's assume the current goes off after line number 8. After line number 8, we've just executed the flash log, which means our log now will have start T, TA8, TB8. Now, the content of the disk A and B are still 8 and 8, but actually what we are going to do is we're going to be blind about the content of the disk. If we see a log, we have to process the log. Now, the log entries is like this. It says T was running, T was modifying A and the old value is 8, T was modifying B and the old value is 8, T didn't finish. So that's a disaster, because that means now we are in an inconsistent state. We don't know what was going on. Okay, so what we're going to do is we're going to go and write back 8 in A and 8 in B. And there is 8 in A and 8 in B. So the effect of writing 8 in A and 8 in B is redundant, but we have to do it because we don't know what was going on. Okay, we have to take the old value 8 and 8 and put it back on the disk in A and on the disk in B. Okay. Now let's see actually now making a good use of this. Up till now, this looks like we're not really doing anything. Let's say the current goes off after line number 9. So after line number 9, we've outputted A. So now we are actually at an inconsistent state. The A is 16 and the B is 8 on disk. Now I will go and open the log. Now who's actually doing that? When the database engine crashes, it has mechanism to track that it has shut down not in a graceful way. So it will start the what we call the recovery manager, and the recovery manager will open the log and will see that T was running and it didn't finish because there's no commit yet, because the flush log that happened at line number 8 caused the first, second, and third instruction in the log to go to disk, but we didn't see a commit yet. We didn't go to step number 12 because the current went off after line number 9. So we will see just 3 instructions in the log that says T1 was running and was doing something to A and B, and here are the old values. Now if the current goes off after step number 9, A is 16 and B is 8. So we're going to write back into A 8. So we're taking it back to an old consistent state, which is 8 and 8. And the same thing if actually the current goes off after step number 10. Even though the transaction has finished in terms of number of steps, but we don't know that because we didn't see the commit. Because the first flush log took the first 3 statements in the log from memory to disk, but we didn't write the commit yet because the current went off. So even though A and B is now 16 and 16, we'll put them back to 8 and 8 if the current goes off after line number 10. Now, if the current goes off after line number 12, and we had a chance to put the commit on disk, when we open the log, we will see that T was running, it was doing some stuff to A and B, but it's done. Since it's done, that means it has successfully brought the database engine to a new consistent state, so we don't actually change anything, we just keep it as is, in the log without actually changing the 16 and 16, we'll just keep them there. So this is how we use the undo log to make sure that we are either at an old consistent state or we keep the new consistent state. Now, the recovery manager is a separate component. I already have been describing it and how it works. It starts after a crash and it looks at the logs and it makes sure that it will fix the content of the tables on disk based on the content of the log. So if it has to know what kind of logging mechanism the database engine supports. Some database engines would support just undo logging. So it knows, the recovery manager, that whatever it sees is the old value. So it's going to go and read that value and put it back in instead of any inconsistent value. I already mentioned this, so I'm just going to read it for you. It says, if T is a transaction whose commit record has been seen, then do nothing. T is committed and must not be undone. Otherwise, T is an incomplete transaction or an aborted transaction. The recovery manager changed the value of X in the database to V, the old value. This is the recovery rules for undo logging. Okay, and we already discussed this, so I'm going to skip forward. And this is an example of the processing that happens by the recovery manager to the log. As you see here, if you look at the left log, this is the beginning, and this is what you see when you start them in the database engine after a crash. Start T1, T1 A5, so T1 was doing something, T2 started, T2 is doing something to B, doing something to C, T1 is doing something to D, T1 is committed, so we're happy, T2 is committed, the recovery manager is happy, and then T3 starts, and T3 didn't have a chance to finish. So the recovery manager, what it's going to do is, after it will do an undo to E and F that were being manipulated by T3 by putting 25 in E and 30 in F, it will write abort T3, okay, that this one has been aborted. And that's, by the way, the logs are actually quite useful even for security audits because it tells you what was going on just before a crash, okay. Now, there's one thing about underlogging you have to realize. The log is being appended at the bottom. So T1 started, we wrote it, T2 came later, so we wrote it after it, and it goes like this. But when we are actually undoing things, we will always start from the bottom and go upward. So the point is, I want to go to the closest history to me moving backward in time. And the closest point in time to me after or to the recovery manager or to the database engine after it starts is at the bottom of the log, not at the top of the log. So the undoing of things done by the recovery manager is done from bottom to top, going from the most recent aborted transaction to the less recent aborted transaction, and it goes like this. So we're always processing it from bottom up to get the final correct consistent old state. Now by now you should be wondering about something. If you really thinking as a computer scientist, this sounds like nice, it's doing a trick, I haven't learned this before, I actually can maintain things in a correct way or in a consistent way. But this is going to be ridiculously big. We're talking about recording every change we make to every record or every column in a table. So if I run a statement that's modifying 1000 rows and the table has 5 columns, that's 5000 entries in the log. And the answer, yes, of course, there's a problem there. Okay, actually it's a big problem, as you already kind of figured out. We're talking about these logs going so big that you have a problem just processing them after every crash. Hopefully your database is not going to crash every day, but if it crashes and you start processing the logs, you might find basically what you have is a history of every transaction, every SQL statement from the minute you created the schema till the point before the crash. And that could be hundreds of millions of entries in the log. Okay, so obviously there is a problem there and we need to manage it somehow. So how do we manage this? We're going to look at 2 techniques. The first one we're going to look at in the context of the undo log, and later on we will see the other one. The idea is simple. I will insert in the log markers that tells me when I start processing the log from the bottom to the top, how far should I go up? I don't have to go all the way to check the history of the database from the minute the schema was created. But if I just insert one marker, that's not good enough. So what I'm going to do is I will have a thread that runs in the background that periodically wakes up every predetermined amount of time, say every 5 minutes or every 10 minutes. And it's going to do the following. It's going to tell the transaction manager, don't start any new transactions. And it's going to tell the buffer manager, tell me when all the running transaction will finish. And when that happens, when the buffer manager notifies this thread telling it no more transactions are running, all of them are done, okay, it will write, this thread will write a marker that we call a checkpoint in the log, and this marker is basically saying no one is running. Because if you tell the transaction manager don't start new transactions, queue them until I tell you to run them again, to start running again, and if you tell the buffer manager tell me when all is done, when all the currently running transactions are done, then no one is currently running when you get a notification that no one is running, because no new one will be introduced into the database engine. Then you go to the log and you write a checkpoint, the word CKPT. Now, when you're processing as a recovery manager the log from the bottom, you stop at the first checkpoint you see from the bottom. Why? Because all transactions above it are done. They have committed. Okay, this is the logic here. If there was no crash happening while that is happening, okay, while all of this is going on, okay, so you don't need to check anything above it. You don't have to check the history of the database engine, record by record to see to find out which transaction failed and which transaction passed. Okay, this is what I'm referring to here. So if you look at this log, which is called the log with a checkpoint, T1 starts, T1 is modifying A and old value is 5, T2 starts, T2 B10, T2 C15, T1 D20, commit T1, commit T2. So this thread will wake up, the checkpoint thread will wake up. Let's say it waked up after T1 D20. So it asked the transaction manager, don't start new transactions. And then it told the buffer manager, tell me when the transactions are done. And once it gets a notification, now while that is happening, T1 is finishing, T2 is finishing, so their commits go to the log. And then it gets a notification from the buffer manager telling it, okay, no one is currently running, all of them are done. So it writes the checkpoint. And then it turns to the transaction manager and tell it, okay, continue on. So now the transaction manager will start T3. Let's say while T3 is running, immediately the current goes off. And when the recovery manager starts again, now it has this log in front of it. Now it will always process it from the bottom up, but the point is, what should it be considering? Well, it will look from the bottom all the way to the checkpoint. Above the checkpoint, there is no need to actually check it, because when the checkpoint was inserted, no one was running, so there is no way you could have been leaving the database at that point in time in an inconsistent state, because no one was running. It wasn't a consistent state. So you don't bother about what's above the checkpoint. And as long as you run this continuously every 10 or 15 minutes, you don't have to go through the whole history of your log to figure out where is the transaction that I need to abort as a recovery manager. Now, we will look at something else now, which is the redo logging. So, undo logging brings the database to an old consistent state. Now, redo logging does the opposite. It will bring the database to a new consistent state. This is preferred generally because undo logging, when it aborts a transaction, by the recovery manager I mean, as if it's never there, because you went to the old consistent state. Okay? Now, redo logging, the interesting about it is that you are going to bring it to a new consistent state. I'll tell you one scenario where you can actually see this happening. Let's say you were buying an item from Souq or Jumia or any one of those websites, and you placed the item in the shopping cart, and you pressed checkout, and you input your credit card details, and you input your address, and you press buy. And then the system goes away for a while, and then your browser timeout. Okay? Let's say on the back end, the system received your request and the current went off. That's why the browser timed out. So, the server room had a malfunction in its electricity, and the current just went out on the server. Isn't it nice that if it has received the details of your SQL, basically, because you talk to an application at the back end, the application sends a SQL to the database engine. If the SQL arrived to the database engine, isn't it nice that since it arrived, the database engine can replay the SQL or submitting the SQL to the engine itself, when the current comes back. So when you log into your account in Jumia or Souq, whatever, you see that you've made the transaction and it's going to be shipped to you. And instead of you going back and doing the process again by adding it to your shopping cart, filling in your address, filling in your credit details, and then clicking again buy. Okay, so with undo logging, that's what's going to happen, because when the transaction gets aborted, as if it never happens. So you'll be surprised, like you clicked buy and the browser timed out, and then you go back and you see that in your transaction history on your Souq or Jumia account that you didn't buy this thing, while you think you've pressed buy and you've input all the details. So they are forcing you to resubmit the transaction again, and you do the whole process again. While with redo logging, actually you will not be forced to do it again. It will be done on your behalf when the current comes back to the system and the database engine kind of recovery module starts. Okay, so what we're going to do here, we're looking at the same example, except now we're going to record the new value, not the value. Okay, as you see here in the log, T1 starts, T1 is modifying A and the new value is 16, T1 is modifying B and the new value is 16, and T1 committed. Okay, so now I'm storing the new value. Now, We're still running with the business of von Neumann stuff. So we modify things in memory and then we put them afterwards on disk. Okay? So what we're going to do is we are going to set a rule that helps us a lot with the redo logging. What we're going to do is, let me read, it says before modifying any database element on the disk, it is necessary that all log records pertaining to this modification of X, including both the update record and the commit record, must appear on disk. Okay? So before you touch the table on disk, you have to write what was the transaction modifying. You have to write the new value, and you have to write the commit, which means you have to tell me everything that transaction is going to do from beginning to end, and you write that to the redo log before you actually touch any row in the table, before you do any output. This is the only way we can redo things, because if I am telling you I'm going to redo, I have to redo it correctly, or I have to bring the database engine now to a new consistent state, and I cannot bring it to a new consistent state unless I have all the details. So all the details means everything that the transaction is going to do, and the commit as well, to make sure that it's everything. There's nothing else remaining. And that's exactly what this rule tries to enforce. Okay? So the same example we looked at before. What we're doing here, again, we have a flash log at line number 9 to make sure that we send the log to the disk, but notice that if we issue a flash log, this means nothing else is remaining except the output. Okay? And what we're going to do is, I'm going to send the log with all its details, including what was happening to individual records, as well as the commit, before I start doing any output. So now, with this scheme, I can redo, because I have in my log a history of basically everything that was going to be done later on. If it's not done later on, well, I'm happy. I have the history. I can replay it. Okay? So that's why we need the commit as well here with us before we start to doing any output. Okay? Now let's track through or trace through a number of possible crashes. What happens if the crash occurs after line number 7? Well, after line number 7, I have modified the content in memory. M-A and M-B are modified in memory, 16 and 16, but D-A and D-B, or A on disk and B on disk, are not modified. I haven't done any flash logs, but I'm happy because the content of the database is consistent. It's an old consistent state. Now, what happens after line number 9? This flash log will send the log from memory, which says start T, T is 16, TB 16, and commit T. Now, on disk, A is 8 and B is 8. So the rule is going to be for redo logging, the recovery for redo logging is as follows. If you see a committed transaction, redo it or execute it, because you have everything that this transaction was supposed to be doing, and you don't know if it actually did it or not, so you're going to redo it anyway. Now, in this case, when the crash happens after line number 9, I'm going to redo it, and it's going to be very helpful to the user, because he meant to change A from 8 to 16 and B from 8 to 16, and he didn't have a chance because the current went off after line number 9. But I have the content of the transaction in the log as log instructions, okay? Or as log documentation. So I'm just going to put 16 in A and 16 in B. As long as I can see the commit, then I'm going to do that. Okay? So what I just described is bringing the database engine to a new consistent state. Now, what happens if the crash happens after line number 11? Well, I have already modified A and B on disk, but again, I will force the rule blindly, so any committed transaction will be re-executed, will be also replayed if you'd like. So I'm going to again put 16 in A and 16 B. It's already 16 and 16, but I'm just going to do the replay blindly. Now, there is also another scenario you might want to also make sure that you understand. If the crash happens after line number 10, I have an inconsistent state. A is 16 and B is 8. But since my log has a committed transaction, which is due to the flush log at line number 9, I will put 16 in A, it's already 16, and I will put 16 in B. Okay, so now I brought it to a new consistent state from an inconsistent intermediary state. So here are the recovery rules that I was just describing. You scan the log from the beginning. Now we would like to bring the log to the most updated value. So we're going to go from top to bottom. Unlike the undo log where we went from bottom to top, here we're doing from top to bottom. So we scan the log from the beginning for each log record encountered. If T is not committed, do nothing. Why do nothing? Because I have no idea what was remaining in the transaction, so I cannot replay it. If T is committed, I will write the value of V for database element X, which means I will replay it. I will redo it. Okay. Now, for each incomplete transaction, I will write an abort T record to the log. Okay. To signifies that this is incomplete and I cannot really do anything about it. We already mentioned this, so I'm just gonna move on. These are the same example we looked at before, and I already covered it 2 slides ago, so I'm just going to move on. Now let's see another checkpointing style. The problem with the checkpoint scheme I mentioned earlier is that we were doing something very drastic. We were stopping the transactions from running so that we write the checkpoint statement. And then we continue running. But there is a problem generally with this notion of let's stop things in a database engine. Let's imagine people are buying stuff now, okay? Like we are in the corona pandemic and people are buying gloves and I don't know, Clorox and Dettol, and actually Dettol doesn't work, but whatever, okay? People are buying stuff online and you suddenly stop them and say, oh, I would like to insert a checkpoint in my log, okay? That's not really a good idea, okay? So there is another style of doing checkpointing that enables you to continuously run transactions and also insert checkpoints and also make good use of the checkpoint, which is to avoid checking the log from beginning to end or from end to beginning. Now, this is how it works. Again, we have a thread, a checkpointing thread. It sleeps for a while, say 10 minutes, and then wakes up every 10 minutes. And this is what it's going to do. It's going to ask the buffer manager, who are the threads that are currently running? So it is told, okay, I got these 5 threads by name, T1, T2, T3, T4, T5 are currently running. So it goes and inserts into the checkpoint, into the log, an instruction that says checkpoint and between brackets T1, T2, T3, T4, T5. Okay? And then it tells the buffer manager, tell me when these 5 guys are done. Now after these 5 guys, others will come, but it doesn't care because when it asked, it was told T1, T2, T3, T4, T5 are running. So it's going to tell the buffer manager, tell me when these 5 are done. And the buffer manager, when the 5 are done, will tell the checkpoint thread, okay, the 5 are done. So it inserts an end checkpoint. Now, how will this play? Because this sounds like risky. Let's see a track of this. So here is an example. Let's say the checkpoint thread waked up just immediately after T2 B10. So transaction T2 modifying B and the new value is 10. So it asks the buffer manager, who's currently running? So it's told T2 is currently running. So it inserts in the log start checkpoint with T2 running. And then it's going to tell it, okay, tell me when T2 is done. And it keeps waking, it doesn't go to sleep yet. Now, you see what's happening afterwards. T2 is doing something to C and the new value is 15. T3 starts, T3 is doing something to D, and then commit T2 comes. The buffer manager notifies the checkpoint thread that T2 has just completed, so it immediately writes in the log this checkpoint thread end checkpoint, and then it goes to sleep. Okay? And this is going to happen again after 10 minutes, and after 10 minutes, and after 10 minutes, and so on. Now, what's the benefit of this? When you're talking about checking the logs, if it's a case of a redo log, the recovery manager will do the following. When it opens the logs, it will start from the bottom, going up all the way till the first start checkpoint it encounters from the bottom. So we could have, because this is going to be continuously done to the log, every 10 minutes we have this start checkpoint, we could have like 100 of them. But we are just interested to find the last one, the number 100, the 100th checkpoint, which is going to be at the bottom. Okay? Now, we will search for it from the bottom all the way till the top, till we find it. In this case, when we do that, what we're actually going to find is start checkpoint T2. So let's think carefully about what does this mean. It means at this point in time, when the checkpoint thread asked the buffer manager who's currently running, it was told T2 is currently running only. No one else was running. So my concern as a recovery manager from now on will be about T2 and other ones that started later on below it. Anyone else that started and finished and was not in memory. So when I asked as a thread as a checkpoint thread who's running, I wasn't told about it. Like I wasn't told about T1 because it was already gone. So I don't need to even look at T1. Okay? Because if it was running, I would have been told. I would have been told T1 and T2. But if I'm told T2 only, then T1 was not running. So I don't need to check anything above the start checkpoint, because anything above it has finished. Okay? So my worry now is going to be T2 and the rest, which is C2 and T3, and we apply the logic that we have described earlier about them. Okay? Now, sometimes when you look at these logs, the redo logs, you will see the commit T2 and the end checkpoint are reversed. Okay? Because they actually happen immediately one after the other, and because of threading, you don't have control on the context switching, so you might have them kind of flipped, so you don't know did you actually, usually it means that you just what you're saying is the result of a context switch. So it would just happen that you were trying to write end checkpoint, I mean the checkpoint thread, and the commit T2 was being written, so one of them came before the other. But the point is, you're not going to insert it unless you're told by the buffer manager that T2 has committed, and you're going to check T2 and what came afterwards. Everything above it, you just completely ignore it. Okay, and this enables you to continuously support transactions without having to stop and queue them as we described earlier. Now, which one is better? We said redo logging helps the user avoid filling in forms, avoid resubmitting data, but it has a little bit of a problem. The problem is we are waiting to write everything to the log in the redo log case before we do anything in the transaction, any physical change to the disk. Okay? And that means that these pages are going to stay in the buffer manager for a longer period of time until we're done with writing the redo log on disk to start writing them from memory to disk. So if a transaction opens 12 different pages and they are modified inside the buffer manager, they will stay there until we get a notification or we understand that this transaction is not going to do anything else. Then we go and write all these changes to the log, to the redo log, and then we put it on disk with its commit, and then we start flushing these 12 pages from memory to disk, which means that we are keeping more data in memory with redo logging. Okay? But we cannot avoid that. Okay? Now, the undo logging, obviously, biggest drawback is you are working always with old data. So users, especially in interactive systems, will be upset that every time the database crash, they have to refill what they were doing, they have to redo what they were doing, they have to submit the form again, fill in the shopping cart again, and so on. Okay. So for that purpose, most database engines implement both of them, so that if you cannot redo, you can undo. Okay, or if you cannot undo, you can redo. And the logic is combined. So the first thing is, inside the log, what we're going to do, we are going to store this transaction is modifying this record, and this is the old value, and this is the new value. So we keep track of everything basically. And we will set one simple rule, which is that, let me read, it says, before modifying any database element on disk because of changes made by some transaction, it is necessary that the update record appear on disk. Notice that I'm not referring here at all to the commit because I have the old and the new. If I happen to see the commit, I will do a redo. If I don't see the commit, I will do an undo. So it's the combination of everything we've discussed before. Okay? So I don't really care about when the commit appears. Hopefully it will appear, so I can do a redo. Okay? And this now becomes our picture, again for the same example. As you notice on the right, the log now has two values. T is modifying A, and which is the second line in the log, and the old value is 8 and the new value is 16. Okay? So let's say the crash happens after line number 8. So line number 8, I have in the logs 3 statements: T started, TA8 16, TB8 16. Since I don't see a commit, then I'm going to do an undo. Let's say the crash happens after line number 10. Now, in the first case I was just describing, there was really no inconsistency because A and B on disk are 8 and 8, but I'm just going to put 8 and 8 there. As we mentioned before, we do it blindly. Now, let's say the crash happens after line number 10. So in line number 10, actually after line number 10, we have an inconsistency on disk. The A is 16 and the B is 8. But after line number 10, I happen to have the commit there in the log. So I will do a redo. I will make the B 16 to bring it to an inconsistent state. Okay, because I can see the commit. Okay. We already discussed, so I'm going to move on. So the recovery for undo redo logs is I'm going to do two passes, a backward pass and a forward pass. Okay, let me read it. It says backward pass, end of log to latest valid checkpoint start. And then you construct a set of committed transactions. The backward pass will follow an undo chain for transactions, which is the active list minus DS. Okay, the forward pass is the reverse. This is basically combining everything we've discussed before, so I don't think I need to elaborate on it more. We're going to do two passes, one from the bottom to the top, doing undo, and one from the top to the bottom, doing redo. Okay, and we stop at the checkpoint. We don't go all the way to the beginning of time, where when we created the schema. We just go to the first checkpoint from the bottom, and this is where we do the undo and redo from. Okay, so again I'm gonna forward. And finally, the takeaway. Logging and recovery is an important feature of a database engine which enables it to protect the integrity of the data from undesired expected events. Logging involves writing down all changes made by a transaction before actually changing values on disk. The log must be written first to disk. There are 3 logging techniques supported by database engines: undo, redo, and undo, redo, together, combined. Each has its own rules and own recovery policy. Now, I have put here for you links to documentation about the logging features in PostgreSQL and SQL Server, and I for sure invite you to go through these pages. Unfortunately, I cannot, I'm not doing I'm not screen recording. I'm using PowerPoint and adding audio to it, so if I go to any other page, the audio recording will stop. But I want you to check these pages because they will show you the details of logging in PostgreSQL and SQL Server, and I want you to inspect these documentation because first of all, you will learn about how logging is done, and you will notice that both of them are having undo redo logs. And the second is there are some parameters you can tweak regarding the log. Like one for example, issue you have to understand is when we talk about logs, we're talking about files that could go into gigabytes. So one of the things that these servers enable you to do is to do what's called log rotation. So you can start the log fresh from a specific date or a specific size. Okay, and there are also some optimizations you can make to the log recording if you're having too much traffic to the database engine, and you would like to enhance the performance of the database engine by making, for example, the checkpoint thread running every extended period of time, for example, every 10 hours instead of every 10 minutes. Okay, so there are certain things you can configure, and they can make the performance in peak times better if you just fine-tune how the logs are recorded. Okay, so read those pages, very useful for you for your career, even that you know about these kinds of tweaks. Not many people know about them unless you've been into the database world. You probably have never heard before about these logs, and you have to understand that they come with a performance penalty. Yeah, we are talking about something that's really nice, really, really impressive in terms of maintaining the integrity of the data, but this has a major impact on performance, and tweaking it is one of the things you should always consider if your database is just slowing down because of excess traffic. And these are the readings that you're responsible for this part of the course.